Okay, so let me start. So this class is going to be full of examples, and then actually towards the end, to state the most general case, we will need the Jordan canonical form. I mean, what we have stated is almost the Jordan canonical form, but um, the most general case will be uh, real and complex eigenvalues. So just to be sure, what we have now is we just have dealt with the case of real eigenvalues. The main new addition is that they need not be distinct. So yeah, so let me, within that category, real eigenvalues, but not necessarily distinct, let's look at some examples. Then, um, real non-distinct eigenvalues. So it's a 2 by 2 matrix, 3, 1, minus 1, 1. In this case, it turns out that you have just a single eigenvalue with multiplicity 2. Well, as I said last time, I think I did this. So last time, as I mentioned this, so what the hell is going on? So, oh, the connection for some reason. Oh, I see. Does anyone know the Wi-Fi password to this? Yeah. Username and password. Oh, IAC. Oh, IAC ID. Then, but what is the password? Oh, IAC password. Oh, great. Okay, fine. That's a pleasant surprise. The pandemic has thrown everything. Well, that's my excuse anyway. Oh, why the hell am I connecting there? Actually, this is uh, yeah, I guess I need Wi-Fi for both, right? So no, I do need to connect there. Well, I also connect here, I guess. I'm sharing my screen. Oh, I haven't even joined yet. Yeah, again, that stuff about making it full screen. So yeah, so the good thing about this is that, well, this happens only in when you have the same eigenvalue, when you just have a single eigenvalue. In any dimension, if all eigenvalues are equal, then of course that S, which is P in general, it's this. In this case, anyway, it's just P2202 P inverse. So this is just a multiple of the identity. So everything commutes. So I'm just left with the same thing. One doesn't even have to figure out eigenvectors in this case. And then once you know S, you figure out so you have A equal to S plus N. You figure out the nilpotent part. That turned out to be 1 minus 1. This. And then, of course, we know that e to the AT will be e to the T times, in general, it will be e to the lambda 1 T, e to the lambda n T, 0, 0, P inverse, and then I plus Tn plus T, T to the K minus 1 into the K minus 1 divided by K minus 1 factorial. Here we just get well, this is just again e to the 2t, e to the 2t. So P will commute. So I'm left with e to the 2t times identity, which I won't write, and then I plus. Now this index of nilpotence that we don't know beforehand. One just has to try. Once you get the nilpotent matrix, you just keep on taking its powers. We know that before we hit n, before or equal to n, we'll get 0. So in this case, well, n is 2. So what can happen is n can be 1, but if n is 1, then the matrix itself will have to be 0. Or rather, if k is 1, then the matrix will have to be 0. But so k has to be 2. So that just leaves me with Tn. And so this will be, so I'll get this matrix, which is 1 plus T, T minus T, 1 minus T. Now, this should not come as a surprise to you. If you have dealt with solving second in some course or another, you would have solved second order linear differential equations with constant coefficients, right? Y double prime plus some constant times y prime plus another constant times y equal to c. If you have taken any course I mean, not in the math course, in say physics. Like I said, if you have to solve for Hooke's law and so on, you encounter second there. There too, you will end up getting some. You'll write down a quadratic equation. You'll solve for the roots. Then there's an issue of what happens. There are two cases will arise: distinct roots, real distinct roots, complex roots, repeated real roots. In the repeated real root case, you will the solution is going to look like a polynomial times an exponential. That is precisely what we have here, except that we have a system. We don't have a single second order equation. We have a system, but we know that one can go back and forth between that and this. So notice that each component of the solution, well, this is not yet the solution. The solution is going to be x of t is as usual e to the at. By the way, sometimes I write t in front of a, sometimes after a. It makes more sense to write in front of a. A is a matrix after all. So the solution will be this. So I have to multiply this whatever I have right here with x naught. But each component, it just looks like a polynomial. Well, in this case, polynomial of degree 1 times an exponential. So but the power of this analysis is that it helps you deal with any size, any n by n system. That second order thing that I mentioned just now, the solution there is, I mean, same thing will carry over in higher dimensions, but things are very simple and you just solve a quadratic equation. It's not clear. If you know that, how to do this is not clear unless you go through this route of exponential and so on. You have to go through the full theory of decomposing a matrix. There's no other shortcut here. In the 2 by 2 case, one can get away with something simpler, even though in our case, even for the 2 by 2 case, we did use the general theory, but it's possible to do it in a more without any theory. The second example is again, well, it's not very enlightening because again, it's the same eigenvalue, but let me just write it since I'm not doing the calculations anyway. The more interesting examples are the ones where you have to compute this generalized eigenvectors. Note that in the previous example or this example for that matter, we won't have to do that. So if one calculates eigenvalues of this matrix, turns out that lambda equal to 1, multiplicity 4. So again, just one eigenvalue. So as before, that the matrix S, which is P times the diagonal matrix consisting of eigenvalues times P inverse, just turns out to be identity in this case, because all eigenvalues are 1. P and P inverse cancel, you're just left with I. And once you know S, you figure out N, which I won't write. But it turns out that now there are three possibilities for the index of nilpotence. N squared can be 0, n cubed can be 0, or n to the power 4 can be 0. And so in this case, it turns out that n cubed is 0. No, actually n squared, n cubed, n to the 4. Yeah, that's right. So it turns out that and once you know this, x of t will be just e to the t, since all eigenvalues are 1, and then just like before, this part is just like what we had at this step, same thing here. So I plus tn plus t squared n squared by 2 factorial, that's it, times x naught, of course. So this actually doesn't shed much light on anything because we didn't have to compute generalized eigenvectors. In the next one, we do have to do that. So this is a 3 by 3 matrix. Note that this is actually, it's an our lower triangular matrix. So you already, the eigenvalue part is easy. So lambda 1 equals 1, lambda 2 equal to 2 with multiplicity 2. Yeah, multiplicity 2. Now, what I was wondering was, even though this eigenvalue is repeated, can we, by just by looking at this matrix, say that it's not diagonalizable? I don't think you can do that. One has to check geometric multiplicity explicitly. Just by seeing the form of the matrix, one can't guess whether it's diagonalizable or not, even if you know the eigenvalues. So, well, for lambda 1 equals 1, I get an eigenvector v1 equals 1, 1 minus 2. And for lambda 2 equals 2, again, I'll get an eigenvector. Point is that we won't get two linearly independent eigenvectors. So I have these two, I need one more. And to complete, get a basis and then form my matrix P. So what we need is actually a generalized eigenvector for lambda 2. So I have to look at this equation, A minus lambda I now, what power should I take? See, we know that in the theorem that I stated, when we look at generalized eigenvectors, we already know the multiplicity of the eigenvalue. And the powers of A minus lambda I that I have to take just go up to the multiplicity, nothing more than that. So in this case, the multiplicity is 2. And so I have to take 2 because if I just don't put any power, I'll get a regular eigenvalue. And I know that I can't have, it'll be just a multiple of V2. But if I put a 2 here and then try to solve this equation, oh well, I might as well put lambda equals to a minus 2I squared v. So this is my equation for a generalized eigenvector. Then, well, you simplify this, you calculate this matrix, square it and so on, and then just solve the system of linear equations. And of course, there's no you don't care about whether there's a unique solution or there can't be a unique solution, first of all. But what you want is you want to find a solution to this which is linearly independent from V2. And that if you play around with this, you can take V3 equals 0 on 0. By the way, a question should arise. See, you know that when you have any number of distinct eigenvalues for a linear transformation in a vector space, and if you look at corresponding eigenvectors, the matrix need not be diagonalizable or anything. All I'm assuming is I'm given a linear transformation. I have k distinct eigenvalues and k corresponding eigenvectors v1 up to vk. Then you can easily prove that v1, v2, vk are linearly independent. Eigenvalues corresponding to distinct eigenvectors are linearly independent. That's independent of diagonalizability or any such thing. It's a simple proof. You start with a linear dependence, take t and so on. So the thing is, that's okay. But so here on the other hand, so that already guarantees that v1 and v2 will be linearly independent. I don't even have to check that. But when I go ahead and find v3, the way v3 has been chosen, it's automatically linearly independent with respect to v2. But what about v1? v3 is not a genuine eigenvector. So I can't anymore say that, well, v3 is a eigenvector for a different eigenvalue, therefore it's linearly independent from v1. So why is that? So I leave it to you to check that. So in fact, of course, that's part of the theorem, big theorem that I stated last time, when you found this collection of generalized that there exists a basis and so on. So it's part of that. It's not, it's saying that there exists a basis of generalized eigenvectors is something more specific than what I'm saying. I'm saying that whenever you take two generalized eigenvectors corresponding to distinct eigenvalues, they will be linearly independent. So you can check this. So if you have
Upon solving this system, taking any v such that v is lambda 1v.
Yes.
We necessarily get that the lambda. Sure. On solving for any lambda, if v is an eigenvector of a with any lambda, then lambda minus 2 whole square.
What do you mean any lambda?
Any.
You're not looking at eigenvalues.
Eigenvalue, any eigenvalue.
Oh, any eigenvalue.
Let's say lambda 1.
And
solve this using the fact that a square b is lambda square b and ab is lambda b. We necessarily get through this equation lambda minus whole square is b. Means lambda has to be b.
Yeah. Oh, that's okay. So what you're saying is that that would prove that if you have a generalized eigenvector, it can't be a multiple of V1, for instance. Yeah, but I'm making a more general statement here. I'm saying that if you have k distinct eigenvalues and V1 up to Vk are generalized eigenvectors, corresponding generalized eigenvectors. So notice that this power k, which are might vary across this V1 up to Vk. Well, I already used k. The powers for the generalized eigenvector equation might change for each of these. So, but if these are generalized eigenvectors, then V1, V2, Vk are linearly independent. This is not so obvious, but you can try to prove it. Yeah, what you said is okay, but here I'm not even assuming any of them is an actual genuine eigenvector. All of them are generalized eigenvectors, which includes the case of eigenvectors, actual eigenvectors. And of course, a generalized one is has that as a subset. Now here, yeah, okay. So short is that anyway, the theorem already told us that actually the way I stated the theorem. Yeah, Pasco is a bit in this point. I think he has omitted something. See, the theorem said there is a basis of generalized eigenvectors in which certain things happen. That A equal to S plus N, where S is P inverse SP and all that stuff happens, right? That is a bit different from saying, and here what are we doing? We are coming up with our own basis of eigenvector, generalized eigenvectors. So a priori, we don't know whether this will work. This basis will do the job, right? By the way, the only place where the basis comes into play is saying that P inverse SP is diagonal. So the theorem says there is a basis which makes S diagonal via P inverse SP. Here, what are we doing? We are just coming up with some basis of generalized eigenvectors. There might be many such things. So there's a priori, there's no reason to expect that this basis will also diagonalize S. So, but of course, in this case, things are simple enough. One can directly check that it does. So P, you form the matrix P equals V1, V2, V3. And then go ahead and then as usual. So S, you find the matrix S by P 1, 2, 2, 0, P inverse. Then find N. And in this case, N turns out to be nilpotent of index 2. So X of t is going to be T exponential of t, exponential of 2t, exponential of 2t, p inverse, and then I plus tn. So the only significance of this example is that we actually had to find generalized eigenvectors. So actually, so now that I mention it, I didn't think of this point that probably it's true that for any basis of generalized eigenvectors, that one has that property that A equal to S plus N, P inverse SP is diagonal, and most important Sn equal to S in S. That's probably true because the way this example has been done, you got hold of the basis. One can of course check that it's this proof is incomplete actually. You got hold of a basis and then you wrote down S, but then you assume the S and N commute everything. So you're basically applying the theorem for this particular basis. So, but what guarantee is there that? So this point I'll check and get back to you. Okay, it's a slightly subtle point that computationally, when you want to use the theorem, you don't want to be. That theorem is just asserting the existence of something which is practically useless. Right? As we know in mathematics, if something exists, then what you can only use it in a theoretical sense. But if you want to actually compute things, you need to know that it should work for every basis, appropriate basis. Now let me, yeah. So the next part of the story is again, let me remind you that when he says complex eigenvalues, he means the imaginary part should not be zero. Complex, non-real. So now the moment you insist that you have only complex eigenvalues in this sense for a real matrix, you're forced to have the size of the matrix to be even, because you know that lambda and lambda bar will have to be there, right? And they'll be distinct. So every eigenvalue comes with its pair. So the size has to be even. And then, of course, as I said, you have the conjugates. This forms a complete set of eigenvalues. But the same issue might arise as in the real case, that there might be multiplicity and there might be multiplicity. So the matrix need not be diagonalizable even over C. So the theorem says that, oh, by the way, this theorem, especially when you deal with complex eigenvalues, the form in which we need the theorem, getting these 2 by 2 blocks, this is not, I don't think I had a look, it's not there in Artin. So if you want to look at it, look at the reference quoted here, Hirsch and Smale, for the proof, if you are interested in the proof of this. It's good to know the proof. It's even better to do it, try to do it yourself before you have a look at this. But if you have not taken a full course of linear algebra, it might be a bit difficult to do it yourself in the first go. At least you should have seen stuff like how to diagonalize symmetric matrices and so on. After a while, if one gets used to that, then one can try to work from scratch. But in any case, you can have a look at Hirsch and Smale. The statement, as far as the statement goes, it's exactly the same as the real case. Then there exists a, again, notice this, there exists, which is a bit troubling. Let me check on this. Then there exists a basis of basis of Cn, no, not Cn, C2n of generalized eigenvectors such that, well, again, you'll take the real and imaginary parts of this, you'll get a corresponding basis of R2n. By the way, did anyone try to see why, when you have a basis, take a basis of Cn of this form, bunch of vectors and their conjugates, C2n, this works only for C2n, even dimensional complex vector space. So when you take a basis of this form, it's quite easy to see that the real and imaginary parts of those vectors form a basis of R2n. Do you see why? It's a very simple-minded argument. When, for instance, why are these linearly independent? U1, V1, etc. UN, huh? No, WJ bar form a basis for C2n.
So look at how UI as a linear combination.
How is it? I mean, that's very easy to say. How you, for example, how is UJ a linear combination of the?
Look at how you written WJ as a combination of Y and VI. That's the main 1I, 1 minus. I think the determinant of that is not. Subtract them.
Yeah, just no, you don't have to do even that much. You just see, after all, UJ is WJ minus WJ, WJ plus Wj bar, that's all. So just like for complex numbers, you express the real and imaginary parts in terms of complex number and its conjugate. So if you have a linear combination of these, you will get a corresponding linear combination of Wj and Wj bars. So that you can read off that all the coefficients have to be 0 and so on. Actually, it's once you prove these are linearly independent, you are done anyway. There are exactly 2n of these. There's nothing more to prove. So it's a maximal set of linearly independent vectors.
That if AI, A1, U1, A2, etc. is 0, then we can write it in a corresponding form of W.
Yes, W and W bars.
Which is 0, but this is non-linearly independent. So
yes, yeah. That's it, yeah. So the rest of the story is the same. So again, you invert it so as to get the right sign in the 2 by 2 block. A equals S plus N, where P inverse SP. Now, yeah, the difference starts popping up here, because now we can no longer expect it to be diagonal, obviously, because P is real, S is real, P, while the eigenvalues are complex. So just as before meaning when we dealt with distinct eigenvalues, we'll get 2 by 2 blocks. AJ minus BJ, BJ, AJ. And N equals A minus S is nilpotent. And NS equal to S. So the corollary for our differential equation is that x of t is equal to t diagonal. Now, when I look at the corollary, remember I'll be exponentiating S. So I'll have to exponentiate the right hand side. And we already seen that when I exponentiate this matrix, I'll get sines and cosines. Oh, I forgot one crucial thing, namely e to the power, exactly. So diagonal e to the AJT and cos BJT minus sin BJT sin BJT, and then you put the P inverse and then multiplied by the exponential of n, which is I plus Tn, t to the k minus 1. So this is exactly the same form as we had for distinct complex eigenvalues, except for this crucial difference that you have this nilpotent part coming in. So this study of diagonalizable, the full study of this group of linear transformations itself is a massive subject in mathematics, Lie groups and Lie algebras. So these things are quite interesting, that how a given matrix can be broken up into different parts. In our case, broken up meant actually sum, but there are other ways also. Even though it's not relevant here, let me just mention one thing. Just like every non-zero complex number can be written as r e to the I theta, right? So every invertible matrix can be written as the role of r. R is a positive number in that case, polar coordinates. Is replaced by a positive definite, what is called a positive definite matrix. And e to the I theta is replaced by a unitary matrix or an orthogonal matrix in the real case. So every invertible matrix can be written as a positive definite matrix times a orthogonal or unitary matrix. This theorem is called the polar decomposition theorem for obvious reasons. It's just like polar coordinates for matrices. That's a very useful theorem. And that kind of decomposition. But for this differential study of differential equations, we don't need, and we don't need that kind of product decomposition is not of much help to us. What helps is precisely what we have written down, a sum where two things commute. So these are all ways of expressing a given matrix into some simpler forms. So, well, there's an example, but again, it's more of the same, except that instead of this example does involve generalized eigenvectors, complex generalized eigenvectors. So it turns out that lambda equals I, lambda bar equals minus I, each one with multiplicity 2 are all the eigenvalues. So how many eigenvectors can we expect? Well, for lambda equals I can expect 1 or 2. It turns out that I just have 1. But once I have an eigenvector for I, then the conjugate will be an eigenvector for minus I. So that's it. So in effect, you just have one eigenvector and its conjugate. So W1 bar. So we need at least 2 more to make our basis. So we have to find a generalized eigenvector for, let's say, I. Again, the power I have to take is forced to be 2 because the multiplicity is 2. So one ends up solving this equation. By the way, the other thing I should mention is, again, just like for eigenvectors, if I find a generalized eigenvector for lambda, the conjugate of that will be a generalized eigenvector for lambda bar, simply because you conjugate this whole equation here. So that's one good thing. You just have to find a generalized one for working with I. No need to repeat the calculation with I bar. And you will get W2 equals, well, this is not the unique one. You can choose W2 to be I101. And then, as I just said, W2 bar will be an eigenvector, generalized eigenvector for lambda bar. So you have your lot W1, W2, and you extract out the right, where were we? Yeah, so U1 is coming from the actual eigenvector 0, 0, 0, 1. V1 is 0, 0, 1, 0. V2 is 0, 1, 0, 1. V2 is 1, 0. So these four will now form a basis of R4. And then you get your matrix P. What I want, the only difference compared to the previous example we did is this S will be P times not a diagonal matrix, but remember it's supposed to be AJ minus BJ, BJ, AJ, where lambda is AJ plus IBJ. But lambda was just I. Yeah. 0 minus 1, 1, 0, 0. Yeah, right. So here the thing is this lambdas. See, when I write it in this form, this blocks might repeat. This blocks on the right hand side might, depending on whether the eigenvalue is repeated or not. So that's what's happening here. That block is getting repeated. So apart from this, there's no other difference compared to the other stuff. So then n turns out n as a minus s, and it turns out n squared is 0. And then of course you write down x of t equal to p. Well, in this case, there's no real part, so I don't have to worry about e to the power anything. So cos t minus sin t, cos t, 0, and the same block repeated here, P inverse I plus Tn. Okay, so I'll stop here. To summarize, so what case, by the way, before I summarize, what case is still remaining? You have covered the. Yeah, mixed. So some of them real, some of them complex, but not real. So surprisingly, that requires this slightly the stronger Jordan canonical form, which I'll state, and or I might just, since I think you got a feeling for this, I might just put up a lecture on you on Teams about that as a separate 1 hour lecture on that. The thing is, how to implement this in practice should be clear. That was the point of today's lecture. Find eigenvalues, find eigenvectors or generalized eigenvectors, enough to get a basis, you figure out P. Once you know P, depending on whether you're in complex setting or all real or all complex, you figure out S equal to P something P inverse. That something is either diagonal or of this 2 by 2 block case. So once you know S, you figure out N, and then you just see what power of N becomes 0. Finally, you put it together as a solution. Okay. So that is the computational point of view, but that's not terribly exciting to know this. The more interesting thing is how to prove all these things. The proofs of these various things that I've been casually using. But even the computational part is, it's a very powerful thing that you are able to deal with any n by n system, at least theoretically. In practice, when you want to do this on a computer, it might be, there's a whole issue of the most efficient algorithm and so on. All right, so let's stop here. I had hoped to give back your exams by this week, but as it so happens, I'll have to give it on Monday, late Monday, Monday or Monday evening. Anyway, it's all on Teams, right? So you will put up grade them by Monday evening. That's the plan.